Alright, so the next force we're going to talk about is dipole-dipole forces, which is between two polar molecules. However, it is not the next strongest. It's actually the fourth strongest. Hydrogen bonding is stronger than it, but we're talking about this one first because hydrogen bonding is a special form of this dipole-dipole attraction. So, again, the whole idea is the attraction between positive and negative. If you've got polar molecules, they have oppositely charged sides or ends. So when the opposite ends get near each other, there is some attraction. Okay? And again, this is also going to depend on, sorry about that, the distance between them. Sorry about that. Okay. Alright, before we talk about this, I want you to notice how this is drawn. Okay, you know these are polar molecules because of the way they're drawn. This is not a representation of an ionic solid. If it was an ionic solid, there would be separate individual ions labeled with charges. These are polar molecules. But they are arranged so that positive and negative are opposite each other. Okay. And of course, they're going to arrange that way to minimize any kind of repulsion, because if the two negative ends get near each other, the two positive ends get near each other, they're going to want to push away. All right, so that's a representation of a solid. The next slide is one of a liquid. So, still arranged to try to minimize the the same sign interactions, but since the molecules are freer to move past one another, there's going to be more of those interactions, so there's less attraction between these than there are between a solid where it's pretty much locked into place. Okay. Questions on dipole-dipole? Okay.
What about in a gas?
Generally, gases, there aren't really many gaseous ions that just naturally occur. They, usually we assume gases have actually like no attraction for each other, so if they are polar, then it starts to mess with like the ideal gas on things. And there are some, but you just don't see it very often. You got to remember the molecules in a gas are so far spread out that there's too much distance for there to be a significant force of attraction between them. It's only if they get close enough to each other that it's something we can actually pay attention to. Alright, so this is our third strongest force, hydrogen bonds, because it's a type of dipole-dipole force. Okay? And I don't like that they name it hydrogen bonds because students hear it and they immediately think that it's bonds between two hydrogen atoms. It's not. It's the intermolecular force that happens when you have a hydrogen bonded to fluorine, oxygen, or nitrogen that then attracts another slightly negative end of another polar molecule. So it's not this attraction between hydrogen and what it's attached to, it's hydrogen and a negative end on another molecule. Okay? So, significantly stronger than any other dipole-dipole interaction. And so, right now we only define it as, capable of happening when hydrogen is attached to one of those three elements. March of this year, scientists actually confirmed that they observed it with hydrogen attached to phosphorus. And I have a link to an article about that I'll post on Google Classroom today. But interesting stuff that they might actually have to adjust the definition of hydrogen bonding. Okay, questions on that? Not just yet. Alright, so here's some important things. I'd highlight these. Why is there such a big difference between a dipole-dipole attraction and hydrogen bonding? It is because the bond formed between hydrogen and one of those three elements is so very polar. Okay? So that means there's going to be a much larger partial negative and much larger partial positive. and those are your three most electronegative elements. Just remember, electronegativity increases across, and it's going to decrease as you go down. So nitrogen, oxygen, and fluorine are your three most electronegative elements. And I found out that we didn't understand on whichever test it was I was grading that noble gases don't have electronegativity because they don't form bonds. Yeah.
Where does that ask?
It's a question where I gave you 4 elements and asked you which one was the most electronegative.
Like when we took yesterday?
Yep. And I had lots and lots of people telling me it was neon of the 4, when fluorine was one of the choices. Fluorine is the most electronegative element. Yes. That happened multiple times. Alright, so hydrogen bonding is very, very important in water. It gives rise to some of the properties that we see in water, namely the very high boiling point. Other things show hydrogen bonding besides water. Alcohols are a common example of this. So methanol, which is a 1-carbon alcohol, is capable of forming hydrogen bonds because you have hydrogen attached to the very electronegative oxygen. So hydrogens on water are going to be attracted to that oxygen, and hydrogens on the alcohol are attracted to the oxygen on water. And this is why water and alcohol, at least the ones up to hexanol, are completely miscible in each other because they can form these really strong attractions.
What does this mean?
They form solutions with each other in any ratio. So like they completely mix. Alright, so next one, acetamide. You can also have hydrogen bonding between, well, it's showing between like molecules. So you've got nitrogen attached to the hydrogen, so then you've got that hydrogen attracted to the oxygen over here. Why that oxygen? Because that's going to have a partial negative charge on it. You've got those lone pairs. Okay, so you could have another hydrogen elsewhere attracted to that nitrogen with its lone pair as well. Okay. Alright, what am I getting to? Alright, so a molecule that does not hydrogen bond. Okay, just because the formula says there is hydrogen and either oxygen, nitrogen, or fluorine does not mean it's automatically going to form hydrogen bonds, because the hydrogen must be attached to one of those 3 elements. And this particular molecule, hydrogen's not attached to the oxygen, it's attached to the carbon. So it does not form hydrogen bonds. Questions on that one? No? Okay, next slide. Alright, interesting graphic. This is boiling point trends, and this really drives home the difference that hydrogen bonding makes. Alright, you've got water and ammonia that experience hydrogen bonding. Okay, significantly higher boiling points. And then when you move on to these other things that do not experience hydrogen bonding, you have the expected trend of, increasing boiling point with increasing mass. But there's a big, big difference. Let's see. Alright, is there anything else I was going to say about that? No. Next slide. Okay, so bringing up potential energy again. Okay, remember, as we decrease the distance, we're going to decrease the potential energy. Yeah, just like we said from the last chapter. Remember, the longer bonds have greater potential energy. Shorter bonds have less potential energy, and those are the ones that are stronger. Okay? So the closer they get, the stronger their bond, the lower the potential energy. I just said this. Potential energy decreases as you get them closer together. And just like intramolecular forces, that you have to put energy into a bond to break it, the same thing applies to intermolecular forces. You still have to put energy into it to break it. Let's see. We can try to get this last a little bit. Alright, so we're on the fifth one. Dipole-induced dipole. If something's induced, it's made to happen. So like, if you induce labor, you force the woman to go into labor. So an induced dipole is something that is forced to become polar simply by being close to something that's already polar. Okay, so polar molecule, nonpolar species. Okay, it's neutral. It has both positive and negative on it. But then when it gets closer to this, it actually attracts the negative part so much that it causes it to temporarily become polar. Now, when you move that induced dipole away from the polar molecule, it will go back to being nonpolar. So I'm trying to think. A big example of this that happens is the reason why oxygen will dissolve in water. It is polarizable, so it's actually can be induced into being a dipole and will dissolve in water. Nitrogen will also do this. Nitrogen can dissolve in water. I have to look. It's towards the end of the week we come back. Alright, so induced dipole, also known as London dispersion forces, or LDF. Okay. Alright, so temporary attractions, and all molecules have this. Okay, remember that's the force that everything has. And what it comes from, the reason why they call it induced dipole is because the electrons are constantly moving around. Okay, at any one given moment, the electrons might be concentrated on one side of the molecule or the other, thus giving it that temporary positive side and negative side. Okay, so by the position of the electrons, it's been induced to become a dipole. Another second, they might be more evenly spaced. Okay. So the next couple of slides are trying to show you that, you know, at 1 second it's this way, the next second it's there. Okay. Those instantaneous changes may give it that polarity at any second. Okay. So, big phrase to remember. The larger it is, the more polarizable it is because it has more electrons. So the more electrons it has, for being a larger atom or molecule, the more polarizable it is. And I guess that's where we're going to have to stop.